All right, so starting with this module and through the next several modules, we're going to talk about failure. So this is chapter 9 in our textbooks. And that's what we're going to talk about today. And the first module is going to look at the types of fracture that can occur. So basically in this chapter, we're going to look at how things break. All right, so this might be kind of obvious, but I do want to sort of start out with why we want to talk about this and what why a part fails, right? Because this is important, right, for kind of post-mortem investigations of airplane crashes, part failures, bridge collapses, things like that, right? So that's what we're going to talk about now. So we want to know, why did the part fail? Was it the design? Right? So that's not necessarily something we think of as material science, but it is important to understand the design of the part. Was it exposed to a larger than expected stress? Right, that is something that we have some control over, but sometimes there's no control. There's kind of larger than designed for. Was it exposed to a different type of stress state than it was intended for? Did it exceed its lifetime? Right, these are all properties that we should be able to know for a given material. Or was there some abnormal temperature or other sort of external factors, right? So these are all kind of things that we need to think about when we look at failure and why things fail. So the main goal is to identify the failure type and then ways to prevent what occurred. So we want to look at what are the different types of failure, under what conditions and situations do those occur, and then we want to know the mechanisms associated with each of those types. So how does it actually fail? And then what are the parameters used to quantify the material's resistance to fracture? So how can we increase that resistance? We'll also talk about. And so those measures taken to reduce the likelihood of failure, right? So we want to look at all of these factors so that we can avoid them, right? So we want to avoid a failure in this case. So this is what the whole chapter is about: failure and how do we prevent it. All right, so we're going to start with what we call simple fracture. So this is when stress is slow. And so this refers to the speed. So it's not some rapid test. It's not, a projectile being fired from a gun or anything like that. These are where stresses are generally slow and the temperature is not abnormally high or anything. It's, room temperature low relative to the melting point of the material. And so we call this sort of static stress because it's slow, and then low temperatures because of the relative melting point. And so the progression of cracks accommodates what fracture. And there's two general types of fracture that we're going to talk about: ductile and brittle. We've used these terms before in the mechanical properties chapter, talking about ductility. So these are already concepts that we are aware of, but here we're going to refer to them in terms of the types of fracture. So they're associated with ductile and brittle materials, but ductile materials can also fail in a brittle nature, and so we'll talk about that as well. So ductile fracture is always going to be favorable because it fails with warning. Because it's not just sudden, right? There's when we talk about brittle, there's not much change in appearance before it fails, and the failure is very rapid and instantaneous. In ductile, we get warning. So with this moderately ductile material and very ductile, you see that it's changing shape, right? The cross-sectional diameter is decreasing here and decreasing to a point in this material, right? So it gives us warning before it's going to break. And so that's one, we get plastic deformation before we get failure. Whereas brittle, there's no plastic deformation, so there's no warning. So in this ductile fracture, we can also identify it based on the necking we've talked about before here and here. And that necking is at about 45 degrees from the tensile axis. So here's the tensile axis, and then 45 degrees, 45 degrees, 45 degrees. That's where we see sort of the maximum shear stress, right? Because that's where the resolved shear stress we talked about before. So ductile, we get slow crack propagation. we have significant plastic deformation, and again, it fails with warning, which is always, if it's something's going to fail, you would like to have a warning. All right. So brittle now is rapid and fails without warning. And so we can identify this because if this is uniaxial tension, the fracture is perpendicular to that axis, and it's usually very smooth surface compared to the more rough ductile surface that we see. And again, brittle, kind of opposite of all those other things, it's rapid crack propagation. There's little to no plastic deformation, and things fail without warning, which again is bad. All right, so let's look at those brittle fracture surfaces. So for brittle, like I said, it's you can see it's perpendicular to the tensile axis. So this is a tensile dog bone. So this is the tensile axis, and then this is that perpendicular surface. And it's not perfectly smooth like a mirror, but it is relatively smooth and 90 degrees. So you tend to get these flat surfaces. You can also get the same thing on glass surfaces, where this is a more magnified image, but this is the fracture surface. This is actually the initiation point, and then you see the smooth portion throughout. But again, it's very smooth, relatively smooth, and perpendicular to the surface. As opposed to ductile, ductile and moderate ductile can be identified by what we call a cup and a cone. So here's the cup because of its shape, and here's the cone. And so this identifies moderately ductile material. So let's kind of look at what leads to this cup and cone fracture. So here's kind of the stages that we see. So we have plastic deformation, and then at that ultimate tensile strength or tensile strength, we get necking. So that's the necking that we see. And the necking progresses, and when we've never really talked about what's happening during necking, but during necking, in the reduced section, in this smaller diameter, what we get is we actually start to get voids nucleating. So voids in the material, so pores nucleating. And so we get more and more of those, and they'll kind of grow and coalesce, which means they're going to grow together. And so you get one big kind of defect here in the middle. And then at a certain point, it fails. So you get basically the crack propagating and breaking the material. And so you get something like this. And so you have that kind of jagged edge from where those voids are, those voids over here. And then over here, you get the fracture, and it tends to be on a 45-degree angle. And this is kind of what it looks like if we look at an SEM or electron microscope image. We see these particles in the material can act as these void nucleations. So these kind of crater-like effects, those are the voids. And then we see that cup and cone structure, right? So this is the 45-degree angle here. So that's where the maximum shear stress is, and that's where it fractures. So you see kind of in here is where you see these void regions with the craters. And then out here, it's relatively smooth because that tends to propagate in a brittle manner on this, but it's 45 degrees. All right, so let's look at some examples of ductile and brittle fracture in a pipe. So here's a pipe, and you can actually see that it's split open down the seam, and you can see it's kind of bulged here. And so that's, again, it bulged, that's warning you that something's happening, right? It's changing shape. And then it kind of just splits down the middle. So it's basically one piece, relatively large deformation, but this would have happened with warning. Whereas if you had a brittle pipe, you get many pieces, and there's lots of small deformations, and you basically have to reconstruct it, right? So this would happen kind of with an explosion, without warning. This is kind of how that would shatter. So that's kind of some examples and the basics of sort of simple fracture, looking at brittle and ductile behavior.